This video is on the objective graph a cardioid from a polar equation. Alright, so these cardioids are a special kind of polar curve, and their equations take on a special form. So it's hoped that when you see an equation with this kind of a form, that you'll be able to recognize it as a cardioid and know what the graph looks like. And cardioid, like here cardio, heart, it's kind of like it's kind of like a heart-shaped graph. You'll see when we take a look at some. So again, if you want to see more about the topic, click on more instruction at the bottom of the question, look at their videos, their notes, their examples, and hopefully those help you. I'll show you some of those notes here. So investigating cardioids. So while translating from polar coordinates to Cartesian coordinates, may seem simpler in some instances, graphing these classic curves, cardioids, we'll see cardioids, things called limaçons, things called lemniscates, and rose curves. Graphing these classic curves is actually less complicated in the polar system, right? So for these kinds of curves, I wouldn't recommend trying to change to rectangular coordinates and then graphing, because they're not going to be that nice. The next curve is called a cardioid, as it resembles a heart. This shape is often included with the family of curves called limaçons, which again I have told you there's another objective in this same assignment where you look at the family of curves called limaçons. Now here we'll discuss the cardioid on its own. Now the limaçon family of curves have these equations. R equals a plus or minus some b times the sine of theta, or r equals a plus or minus b times the cosine of theta. And it's just theta, not 2 theta or 3 theta or 4 theta, just theta. So you have some number plus some number times the cosine, or some number plus some number times the sine. These are limaçons. All right, in general, these are called these limaçons. Now specifically, if a and b have the same magnitude, meaning their ratio is 1, so if a divided by b is 1, if a and b have the same basic value, the same magnitude, then we get a special kind of curve, a special kind of limaçon called a cardioid, which will be kind of like a circle with one side pushed in. Right, you see all these examples. I like to think of them as like little butts. Like, I know it's not very proper, but they look like hearts or little butts. But it's like a circle with one side pushed in on it, so a little dimple, right? And you can see the kind of fat heart shape. It's a big wider heart shape than usual, but that's where the cardioid name is coming from. But these are all when a and b, again, when a divided by b equals 1, when a and b have the same magnitude. And really I should do the absolute value here. And let me show you some examples of these on the, this is that free online graphing calculator called Desmos. Go to desmos.com, free. And let me show you what R equals a plus a, right? Because again, this is a and b are the same thing. A plus a times, say, the cosine of theta. Right? And I'll add a slider for a, and look, see when a equals, no, this is just, a is 1, so this is r equals 1 plus 1 cosine theta. And you see you get this cardioid shape. And I can slide a all over the place, and it's just a bigger cardioid, or a cardioid in the opposite direction. All right. The same thing would go for a minus a, I think, right? A minus a, same thing, another cardioid, and then this is just a cardioid in the opposite direction. All right. As long as these two numbers, if you ignore the negatives, as long as these two numbers are the same, right? I think I could even do this. Right. Yeah. So as long as, if you ignore the negatives, as long as these numbers are the same, some number plus some other number time, some same number times the cosine of theta or the sine of theta, you get this thing called a cardioid. Let me show you the sine version. All right, they're just bigger hearts opening up, hearts that are up and down. Right. Okay, so that's all they're saying here, right? Where you see that a over b equals 1. Again, really technically they should say the absolute value of a over b equals 1. As long as a and b have the same magnitude in these equations, you'll have what's called a cardioid. All right, so let's take a look at this example here. So they're asking us to produce a graph of this function, right? This polar equation. All right, so I'll go to a piece of paper. And we have this equation. We have r equals -7 times the sine of theta plus 7, just a constant. Now if you want to write it in the same form that they had it in the instruction, you put the constant first and then -7 times the sine of theta. But notice that these two have the same magnitude, right? The same magnitude, the same absolute value, whatever you want to call it, right? And if that's the case, the graph of this thing is going to be one of those cardioids, or those heart-shaped graphs or butt-shaped graphs. Right? So I know what the graph's supposed to look like. Right? I just want to know, I want to well, now let's just graph it and see if I do get that shape. Alright, so first I'm going to start graphing it. I'm going to do this by hand, and then I'll just go to the calculator, the Desmos calculator, and show you a prettier picture. So if you've seen some other videos, I've done some other videos where I've graphed, polar equations by hand, and they can be a bit tricky. But what I like to do for a lot of these is go to what I call the XY version. Now this is not rectangular. I'm not saying convert to rectangular coordinates. This is just replace r with y, replace theta with x. So I have y equals -7 times the sine of x plus 7. So everywhere there's an x, I think of it as theta. Everywhere there's a y, I think of it as r. And I'm just going to graph this the way we normally graphed trigonometric functions back in previous chapters. So here's x, here's y. Again, y represents r, values of r. X represents values of theta. Now this is not the polar grid, right? I'm gonna go to the polar grid after this and fully graph this in polar coordinates on the polar grid. All right. Well, this would have a period of 2 pi. So I'll go from 0 to 2 pi here. Cut this into quarters. All right. And then sine of 0 is 0, and the highest this is gonna get is remember y equals 7 here is going to be the midline. The lowest they'll get is 0, and the highest they'll get is 14. Trust me, right? Because the amplitude is going to be 7. The midline is going to be at 7. Now the sine of 0 is 0, and then plus 7. So we start at the midline here. Sine of pi over 2 was 1. -7 plus 7 is 0. And then you go back to the midline at pi, and then the highest point at 3 pi over 2, 14 there. And then back to the midline at 2 pi, and here's this curve. And I'm not going to go into how I got this, right? You should know how to graph your sine and cosine functions by now. I'm going to use this graph here as a guide when I go to graph the polar curve, on the polar grid. All right, so I'm going to cover this up for now, and let's make a polar grid. All right, so you have a vertical axis, which really does nothing, right? It means nothing. And the horizontal axis, which is that polar axis. And I noticed in my graph here, the largest value of r, or y, is 14. Right? So I'm going to go on the polar axis out to 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's, and then I noticed some other values of 7 and 0 came up. Right? 0 is at the pole, and then 7 is here. Right? Yeah. And I'll draw these circles, right? Remember, we're on the polar grid. We're traveling in circles around the pole, around the origin. So here's a circle with a radius of 1, very, very tiny. Circle with a radius of 7. And bear with me here, this isn't the greatest looking thing in the world. My circles aren't perfect. And then a circle with a radius of 14. Okay. All right. And then, I'll mark off all these angle measures as well. On the x-axis, these are values of theta. Theta equals 0 corresponds to being on the positive side of the polar axis. Theta equals pi over 2 corresponds to being on the positive side of the vertical axis. Theta equals pi corresponds to being over here on the negative side of the polar axis. Theta equals 3 pi over 2 corresponds to being down here on the negative side of the vertical axis. And then theta equals 2 pi. You're right back to where you started from. So when I go through this graph, I should get the entire picture, right? Because I've gone once around my polar grid. Going from 0 to 2 pi here should give me the entire polar graph. All right, so let's take a look at what happens. All right, so in this piece of the graph up here, right, my xy version, see how the value of r went from 7 to 0. And my theta went from 0 to pi over 2. So I'm in the first quadrant, and the values of r are all positive, so I'm going to stay in the first quadrant. Remember, if they were negative, I'd be drawing my graph in the third quadrant, the opposite side of the circle, where r's would be opposing. Right? Opposite values of r take you to the opposite side of the circle. So I'm starting when r equals 7, theta equals 0. So that's this point here. R equals 7. Theta equals 0. And then I'm ending at, r equals 0, theta equals pi over 2. And I'm drawing all this, and the values are going down, and this is all in the first quadrant. And then having an r of 0 is the origin. And I'll say it does something like this. Right. So r equals 7, 2r equals 0, all in the first quadrant here from theta equals 0 to theta equals pi over 2. Again, I'm making very rough sketches. Then on this piece of the graph, between these 2 points, I'm between pi over 2 and pi, so in the second quadrant. The values of r are positive, so I'm still going to graph in the second quadrant. And I'm going from r equals 0 up to r equals 7, so it's kind of like that again. I'm increasing until I get to r equals 7 at theta equals pi. So it's like the other part of the heart shape or the butt shape, right? And there's a little dimple, This is like the pushed in side of the circle. All right, then from pi to 3 pi over 2. So I'm in quadrant 3. Again, values of r are positive, so my graph is going to be in quadrant 3 and not on the opposite side in quadrant 1. And I'm going from r equals 7 to r equals 14. So I'm starting here and ending here at 3 pi over 2, 14. And I'll just keep this curve going. And don't draw a straight line, right? This is all curvy. The radius increases in a smooth curve, so something like that maybe. And then the rest of the way, 3 pi to 2 pi, I'm in quadrant 4. Values of r are positive, so my graph will be in quadrant 4. And I'm going from a radius of 14 to a radius of 7. So from this point to that point again. And then just a nice, again, don't draw a straight line, but just a nice smooth curve. And there's your cardioid. Well, kind of a heart shape going on. All right, this is a very, again, rough sketch by hand. Let me show you on the Desmos site that same curve. Oh, this was from an older video, sorry. R equals, we had 7 minus 7 times the sine of theta. And look at this, and I'll zoom this out. And I'll draw in my circles with a radius. I had a circle with a radius of 7 that we kept landing on, right? And a circle with a radius of 14 that we kept landing on. Right? You see these points, right? these points here, radius of 7, this point here, radius of 14. So there's your cardioid. And similar to, much prettier of course, but similar to the shape that I drew by hand. Alright, so going back to here, which graph am I choosing? Well, not that one. Now this is a cardioid. But you gotta pay attention. Remember these points on the polar axis, they need to be on a circle with a radius of 7. Well, they're not. They're on a circle that would have a radius between 3 and 6. So this isn't the cardioid I want. How about here? This point, yeah, that's between 6 and 9. This point and this point need to be on a circle with a radius of 7. This point at the bottom needs to be on a circle with a radius of 14, which it is on the circle between 12 and 15. This looks like the cardioid that I want. Yeah, so I'm going to select that one. Okay. And again, you could just go to the Desmos site and punch this in and look at the picture there. Just make sure you know which cardioid, right? Because there were a couple cardioids as options. Right? You had to pay attention to how far away from the pole, how far away from the origin certain points were. Okay. All right. So hopefully watching me do this, playing around on Desmos, looking at the more instruction when you need to, reading the answer explanations when they come up. Right? I'm hoping all this stuff helps you out when you're working on this material on your own. All right, and thank you very much for watching.